Hello my dear students, welcome back to my channel. Today with this video, I will cover all important topics and formulas of chapter 3, that is current electricity. What does it mean? Current electricity means study of charges in motion. When the charges are in motion, it produces current. So different topics to be covered in this chapter are, first one is electric current, then drift velocity and Ohm's law, resistance, electrical energy and power, electrical resistivity and conductivity, temperature dependence of resistance, the internal resistance of a cell, potential difference in EMF of a cell, combination of cell in series and panel, Kirchhoff's law in its application, Wheatstone and meter bridge, at last potentiometer, its principle and its application. So let us start first with what do you mean by electric current. Current electricity means study of charges in motion. Electric current, when the charge are in motion, then what happens? How much charge flowing through a particular cross-sectional area of a wire. That rate of flow of electric charge or electron through any cross-section of a wire is called electric current. Formula is given by I equal to Q by T. SI unit of this current is ampere and it is a scalar quantity. So 1 ampere equal to SI unit of charge is 1 coulomb and time is 1 second. So 1 ampere equal to 1 coulomb in 1 second. You can define 1 ampere from this formula also. Now from the quantization of charge, Q equal to NE. Q is here what? 1 coulomb. E is charge of electron. Then what is the value of number of electrons in 1 coulomb? There are N equal to 6.25 into 10 to the power 18 electrons in 1 coulomb. You must remember this one. How much number of electrons? 6.25 into 10 to the power 18 electrons in 1 coulomb. Now what is direction of electric current? Actually it is a scalar quantity, but it has direction because it does not follow vector law of addition. So it is not a vector quantity, it is a scalar quantity. But direction of electric current is direction of motion of positive charge. It means opposite to the flow of electrons. It means from positive to negative terminal of the cell. Suppose this is a cell. This one is positive terminal, this is negative terminal. Direction of current is from positive to negative terminal. And electron flows from negative to positive terminal. So direction of current is opposite to the direction of flow of electrons. You must note one thing here, that in a metallic conductor, current flows due to motion of free electrons because inside a conductor large number of free electrons are present. While electrolytes and ionized gases, current flows due to electrons and positive ions, right? After this, next is, there are two types of velocity inside a conductor. One is thermal velocity of free electrons, another one is drift velocity of free electrons. Now what are these two? You know, inside a conductor, electrons move randomly in all possible directions with maximum highest speed. That is called, how much speed it moves? 10 to the power 5 meter per second. This speed is called thermal velocity of free electrons. Suppose this is a conductor. Inside this conductor, large number of free electrons are present and they are randomly moving in all possible directions. So the velocity with which it moves without application of any electric field or potential difference, that velocity is called thermal velocity. And its value is given by 10 to the power 5 meter per second. And average thermal velocity of free electrons in any direction remains 0 because they are not moving in a particular direction. So net velocity is always 0. You must remember this point. Average thermal velocity of free electrons is always 0. Now, when this conductor is connected to a cell, cell means potential difference is there, and due to that potential difference, electric field is set up through this conductor. Now what happens when cell is connected to this conductor, electron starts moving towards this positive terminal of the conductor, right, in a particular direction. So when a potential difference is applied across the ends of a conductor, the free electrons moves with an average velocity opposite to the direction of electric field. Electric field is in this direction, positive to negative. Electron moves from negative to positive, opposite to the direction of electric field. That drift is called drift velocity of free electrons. Now what is the value of this drift velocity? It is Vd equal to electric field E is applied. So E tau by m. Here E is charge of electron, E is electric field applied, right? Now, tau is relaxation time between two collision and m is mass of electron. All the terms are written here. And also you know one relation E equal to V by L. So you put the value of E here, you get drift velocity in terms of V also. So you must remember this formula, Vd equal to EV tau by ml. Next, what is the relation between electric current and drift velocity? It's very important. relation between electric current and drift velocity is because due to drift velocity, electric current is produced inside a conductor. So this current I is given by NEAVD. I is equal to NEAVD. N is number of electrons, E is charge of electron, A is area of cross section, VD is drift velocity. And when you put the value of this drift velocity in this equation, you get NE square AE tau by M. And in terms of V, when you put this VD, NE square AV tau by MS. So you just remember one formula, that relation between current and drift velocity is this one, very very important. I equal to NEA VD, and VD you know in terms of E also, in terms of V also. In this way you get relation between I and VD. After this, next topic is current density. What do you mean by current density? You know current is a scalar quantity, so to show its direction, this current density term is used. Electric current flowing per unit area of cross section of conductor is called current density. It is represented by J, and J is equal to I by A. Its SI unit of current is ampere, area is meter square, so ampere per meter square, and dimension formula is A L to the power minus 2. This current density is a vector quantity, and direction is in the direction of motion of positive charge or in the direction of flow of current. So to show the direction of current, this current density is used. It is a vector quantity. Next, mobility. What do you mean by mobility? When electric field is applied across the ends of the conductor, electron starts moving with some velocity. That velocity is called drift velocity, and that drift velocity of electron per unit electric field applied is called its electric field. It is represented by mu. This mobility mu is equal to Vd by E. Great E is directly proportional to Vd now, right? If electric field is strong, electrons moves with higher speed, so E is directly proportional to Vd. When you remove this proportionality constant, you get E equal to mu Vd, and this mu is called mobility, E by Vd. So drift velocity of electron per unit electric field is mobility of electron. Its SI unit is meter square per second per volt, and its dimension formula is M minus 1 T square A, right? Ohm's law. What is this Ohm's law? According to this law, if physical conditions of a conductor, it's very important, such as temperature remains unchanged, then electric current flowing through the ends of a conductor I is directly proportional to potential difference V applied across its ends, right? So I is directly proportional to V, or you can write V is directly proportional to I. So V equal to Ri. R is a constant called electric resistance of the conductor. Its value is given by R equal to A NE square tau by M. And A is area of cross section, N is number density, E is charge of electron, M is mass of electron, L is length of the conductor. So this is scalar form of Ohm's law, right? Now, how you write this vector form of Ohm's law? You just replace simply some terms from this scalar form. This V is a scalar quantity, so in place of V you can write E. This I is a scalar quantity. In terms of this I, you can write vector quantity J. And this R is a scalar quantity. In terms of resistance, in place of resistance, you can write resistivity rho. So scalar form of Ohm's law becomes E equal to J rho. J is current density, rho is resistivity, E is electric field, right? And reciprocal of this resistivity is called conductivity sigma. Electrical conductivity sigma is reciprocal of resistivity. So if you replace this one, it becomes E equal to J, rho is what? 1 by sigma. Then equations become J equal to sigma E. So J equal to sigma E or E equal to rho J. These two are vector form of Ohm's law. J equal to sigma E and rho J equal to E. This SI unit of this resistivity is ohm inverse meter inverse, or Maho meter inverse, or you can write Simon meter inverse also. Now after this, next, electrical resistance. What is this electrical resistance? It is obstruction offered by any conductor in the path of flow of current. This is electrical resistance. Its formula is given by R equal to V by I. Its SI unit is ohm. Its dimensional formula is M, L to the power 2, T to the minus 3, A to the power minus 2. And electrical resistance of a conductor in terms of resistivity length area is given by R equal to rho L by A. This resistance depends on length of the conductor, area of cross section of the conductor. This rho is called resistivity, and it is independent of length and area of the conductor, right? It only depends upon temperature and nature of the conductor. Why this resistance? From where it exits? If large current flows through a circuit, what happens? It will damage the circuit because large amount of heat is produced. So resistance helps to avoid this damage and controls flow of current. So it is produced inside the conductor by itself. Now, why this resistance depends on length and area? If length of the conductor is increased, number density is fixed, number of electrons in the metal is fixed. If length of the conductor is increased, it means these electrons collide more with the positive ions, right now, and hence more collision means more resistance. Resistance is directly proportional to collision. So greater the length, greater is the collision, greater is the resistance. What happens if area is increased? If area is increased, it means electrons requires more space to move. So there is less number of collision. So that's why less resistance. So resistance is inversely proportional to area. And when you combine length and area, you get R is directly proportional to L by A. So R equal to rho L by A. Rho is resistivity. Resistivity of a material of a conductor is given by rho equal to m by Ne square tau. M is mass of electron, N is number density, is charge of electron, tau is relaxation time. Resistivity of a material, it does not depend upon length and area, na? It is independent of dimensions of the conductor, length, area, cross section. How this resistance and resistivity depends on temperature. Temperature dependence of resistance and resistivity. You know, formula for resistance is what? R equal to rho L by A, and resistivity is rho equal to m by Ne square tau. So R is directly proportional to rho, and both are directly proportional to mass of the electron is constant, charge of the electron is constant. So inversely proportional to n tau. N is number of electrons per unit volume, tau is relaxation time. So how this resistance depends on temperature in case of metals, semiconductor and alloy. In case of metals, what happens? When temperature increases, relaxation time decreases, na? Time of collision between the two is it moves with faster velocities. Its speed increases, so relaxation time decreases. But for metals, N is constant. Number of electrons is always constant in case of metals. So relaxation time decreases, it means resistivity increases. So for metals or conductor, graph is like this one. Resistivity increases with the increase in temperature. This side is resistivity and this side is alloy x-axis temperature. Right? Now for semiconductor, in case of semiconductor, what happened? Again same thing, when temperature increases, relaxation time decreases, time of collision increases, yes, relaxation time decreases. But in case of semiconductor, electrons are tightly bound. So these electrons move freely when temperature increases. So N also increases. Here N increases much more than tau decreases. Right now value of N is larger than tau. Hence what happens? When N increases, this resistivity decreases. So graph for semiconductor is like this one. When temperature increases, resistivity decreases. And in case of alloy, again here resistivity increases with increase in temperature, but its increase is very much small as compared to metals. So these are graphs for how metals, semiconductor, alloys, time resistance and resistivity depends on temperature. Now what is the relation between this resistance, temperature? At any temperature, relation between resistance, resistivity, temperature is given by this equation. RT equal to R naught 1 plus alpha T, where R naught and RT are resistance of metal at 0 and T degrees Celsius. This alpha is called temperature coefficient of resistivity. It's very, very important. From this equation, alpha becomes RT minus R naught by R naught T. This formula is used in numericals when you solve numerical. So you must remember this formula, alpha equal to RT minus R naught by R naught T. Now in case of metals, what happened? Resistance or resistivity increases with increase in temperature. It means for metals, this alpha is positive. For alloys, again resistivity increases, but increases less than that of metals. So again it is positive for alloys also. For semiconductor, resistivity decreases with decrease in temperature or resistance. So alpha is negative. You must remember this point. For metal, alpha is positive. For alloy, alpha is positive but less than that of metal, and for semiconductor alpha is negative. So there is one important point, you must note down this one. Resistivity is low for metals, more for semiconductors and very high for alloys like nichrome, constantine, etc. Right? Now there are some limitations of Ohm's law. You know, graph with when physical conditions remains constant, the graph between V and I is what? It is a straight line. This side V and this side I, and it is a straight line. So this follows Ohm's law, right? But for metals like semiconductor or diode, this VI graph is not a straight line, it is a non-linear graph. For semiconductor, it is like this one. Graph is like this one, not linear. So it does not obey Ohm's law. These are limitations. For autovoltmeter also Ohm's law not true. So there are two types of substances based on who obey Ohm's law and does not obey Ohm's law. Ohmic conductor and non-ohmic conductor. Ohmic conductor are those conductors which obey Ohm's law. It means graph is linear. Right now, non-ohmic conductors are those conductors which do not obey Ohm's law. So graph is non-linear. Example: semiconductor, diode valve, triode valve, transistor, etc. Here VI graph is not a straight line. After this, next topic is combination of resistors. This is not in your syllabus, but still you know what is the equivalent resistance in case of series and parallel combination. Series combination equivalent resistance is given by R equal to R1 plus R2 plus R3. Here current is same in each resistor and sum of potential difference across each resistor is equal to potential difference applied by the source. It means V1 plus V2 plus V3 is equal to V, and here current is same in through all the resistor. So equivalent resistance in series combination is R equal to R1 plus R2 plus R3. In case of parallel combination, one end of each resistor is connected to one point, other end of each resistor is connected to another point. This type of combination is called parallel combination. Here potential difference is same across all the resistor V, but current is different across different resistor. So total current, sum of current flowing through all the resistor I1 plus I2 is equal to total current drawn from the source. So these are two types of connection, series and parallel. You must remember equivalent resistance in case of series and parallel. These are helpful when you solve numerical. Then next, electric cell. What is this electric cell? You already studied in chemistry. It is a device which converts chemical energy into electrical energy. It has two electrodes, one is cathode, one is anode. It means one is positive, one is negative. Positive one is bigger and negative one is smaller. Now different terms related to this electric cell: electromotive force, EMF of the cell, terminal potential difference of a cell, and the internal resistance of a cell. This is a cell having two terminals. This symbol for cell, positive and negative. It has internal resistance small r, and current I is flowing through this circuit. When the circuit is closed, external resistance R. These are different terms. What is this EMF of a cell? This is a cell having internal resistance R. When it is not connected to the circuit, it means no current is flowing through the circuit. Circuit is open. At that time, maximum potential difference between electrodes of the cell is called EMF of the cell. And when the cell are using, it means when the circuit is closed, current is flowing through the circuit. At that time, the potential difference between terminals of the cell are called terminal potential difference of a cell. Both have unit volt. This E equal to W by Q. V is also W by Q. This V is when the circuit is closed through the external circuit. At any time, potential difference between terminals of the cell is V. And when the circuit is open, when no current is flowing, at that time maximum potential difference between the terminals of the cell is called EMF of the cell. Right? EMF of the cell is the E, and terminal potential difference is represented by V. When the cell are using, it means there is discharging of cell, and during discharging of cell, E is greater than V, and during charging of cell, direction of current is reversed. In that case, E is less than V. Then next, internal resistance of the cell. What is this internal resistance? Cell has some electrolyte solution. It depends upon what type of electrolytic solution you are using. So internal resistance depends. Internal resistance of cell is opposition of the electrolyte of a cell in the path of electric circuit. It increases with increase in concentration of the electrolyte, increases with increase in distance between the electrodes, and also decreases with increase in area of electrodes. All these factors depends: concentration of electrolyte, distance between the electrodes, and area of electrodes. Now one more important thing, very important, note down this one: relation between E, V and R. What is relation between EMF of the cell, terminal potential difference and internal resistance? So E equal to V plus IR. E is EMF of the cell and this E is divided in the internal resistance right now. So V plus IR. From here you get R equal to E by V minus 1 into R. So this is during discharging of cell. When the cell is discharging, relation is E equal to V plus IR. It means E is greater than V. But when the cell when the cell is fully discharged, then you have to charge the cell, and during charging, direction of current is reversed and relation becomes E equal to V minus IR. In this case, E is less than V during charging of cell, right? Okay. Then next grouping of cells, there are two series combination and parallel combination like resistors. In series combination, if large number of cells are connected in series having internal resistance R1, R2, R3, then equivalent EMF of the cell in case of series combination is E1 plus E2 plus E dash dash dash. If all have same EMF, then E equivalent equal to NE. Equivalent internal resistance of the cell is given by R equivalent equal to R1 plus R2 plus R3 dash dash dash. If all have same internal resistance, then R equivalent equal to NR. If there is some external resistance in the circuit, then current in the circuit is E equivalent by total resistance is R plus R equivalent right now. So this is series combination. In parallel combination, if suppose large number of cells are connected parallelly, then E equivalent is equal to total EMF of the cell, and 1 by R equivalent equal to 1 by R1 plus 1 by R2 plus 1 by R3. If all have same resistance, then this is equal to R equivalent equal to R by N. This one is very important relation. Current in the circuit is I equal to E by R plus N. So you must know about series and parallel condition. One important point, current in this circuit will be maximum. This may generally ask MCQ type questions. When the current in a circuit is maximum, when external resistance is equal to equivalent internal resistance, then in that case current is maximum in the circuit. After this, next is electrical energy and electrical power. Electrical energy is the amount of work done or energy consumed in a given amount of time. Its formula becomes equal to I square RT equal to V square by RT equal to VIT. There are three forms of electrical energy. It's a sign it is measured in joules or watt RWH, or commercial unit of this electrical energy is kilowatt hour. 1 kilowatt hour is equal to 3.6 into 6 joule. Next, electrical power. At what rate this electrical energy is dissipated right now? So rate at which this electrical dissipated consumed in a circuit is called electrical power. You just divide by electrical energy divided by this rate. It means time. You get power. So I square RT divided by T is I square R. So power equal to VI equal to I square equal to V square Y. There are three forms of power. So unit of power is what? 1 watt is consumed when 1 ampere of current flows through a device at a potential difference of 1 volt. So next, Kirchhoff's law. There are two Kirchhoff's law, Kirchhoff's first law and Kirchhoff's second law. To solve complicated circuit, these Kirchhoff's law are used. Kirchhoff's first law is also called junction rule. The algebraic sum of all currents meeting at a particular junction in a closed circuit is always 0. It means total current is always 0. Total incoming current is equal to total outgoing current, and this is also law of conservation of inner charge. This Kirchhoff's first law follows law of conservation of charge. Now second law, Kirchhoff's second law is also called loop rule. The algebraic sum of all the potential difference in any closed circuit is always 0. It means total potential difference across any closed surface is equal to 0. It means E equal to IR. Total EMF of the cell in the closed circuit is equal to product of current and resistance along different branches, and this follows law of conservation of energy. So you must remember these two laws, Kirchhoff's first and second, junction rule and loop rule. Junction rule is related to conservation of charge, and loop rule second law is related to conservation of energy. Very, very important. Next, Wheatstone bridge. What do you mean by this Wheatstone bridge? This Wheatstone bridge is also known as meter bridge or slide wire bridge. This what is this? It is an arrangement of four resistance P, Q, R in this diagonal form. Here galvanometer is connected along one diagonal and cell is connected along another diagonal. Now when this galvanometer shows zero deflection, it means the bridge is balanced. In that case, P by Q equal to R by S. When no deflection in the galvanometer, then the bridge is said to be balanced, and under balanced condition, the ratio of resistance across the four arms are equal. P by Q equal to R by S. If you know three resistance, you can easily find the fourth unknown resistance with the help of this Wheatstone bridge. And this bridge is most sensitive when all the four resistance are of the same order. Now, then next is meter bridge. What is this meter bridge? It is simplest form of Wheatstone bridge and is used for comparing resistance more accurately. It is based on the principle that when the bridge is balanced, P by Q equal to R by S. It is based on Wheatstone bridge principle. So it consists of one long meter wire, 1 meter length, right now having uniform area of cross section. This in the left gap unknown resistance is kept, in the right gap known resistance is kept. Now using non-deflection method, you have to find this balancing length L1, and this hole is 1 meter. So if one side balancing length is L1, then other this one 100 minus L1. So after using this Wheatstone bridge principle, you get this formula: R by S equal to L1 by 100 minus L1. L1 is balancing length when the bridge is balanced, when no current flows through the galvanometer. If S is known, you can easily find unknown resistance R equal to S L1 by 100 minus L1. In this way, meter bridge, we can determine unknown resistance very easily. Now, next and last topic of this chapter is potentiometer. What is this? It is a device which is used to measure potential difference between two ends. Voltmeter is also a device which is used to measure potential difference, but it gives accurate result. It consists of a long resistance wire AB of uniform area of cross section, and it is based on the principle that when constant current flows through this wire, suppose this wire has length L. If constant current through this EMF of the cell flows through this wire, and then V is directly proportional to L. It means V equal to KL and K equal to V by L. This K is called potential gradient. So if constant current flows through this wire, then V is directly proportional to L. If you know the EMF of this cell, they can easily determine the unknown EMF of another cell. Another cell whose EMF is to be determined is connected to one endpoint of this one, and another point is connected to galvanometer and jockey. Now you move the jockey over this one. When the galvanometer shows no deflection, you note down this point. Then potential difference across this AJ, when no current flows through this, it gives EMF of the unknown cell. It means potential difference across AJ is equal to E, and this is equal to KL. You have to use this formula. In this way, you can determine unknown EMF of the cell. There are two important applications of this potentiometer. One is comparison of EMF of a cell using potentiometer, and another determination of internal resistance of a cell using potentiometer. This is the arrangement for comparison of two cells. Two cells are connected one by one. What you have to do, you know the basic principle that V is directly proportional to L. It means if this is the known cell right now. Now these two are unknown cells whose EMF you have to compare. So first this key is closed. In that case, galvanometer shows no diffraction. So potential difference across this gives first EMF of the cell E1 equal to KL1. Then you open this one and close this second key, in which E2 is in the closed circuit. In that case, find the point where galvanometer shows no deflection. That point, suppose there is another point, and that case gives potential difference across the second cell. It means second EMF of the cell E2 equal to KL2. Now divide these two, you get E1 by E2 equal to Ln by L2. In this way, you can compare EMF of two cells. One last important application of this one is determination of internal resistance of a cell using potentiometer. This is arrangement. This is known cell, key, rheostat, and this one is unknown cell. You know, you can easily determine the EMF of this unknown cell right now. Now you have to find internal resistance R of this cell. So for this one resistance box is used. There are two keys, K1 and K2. First, when this K1 key is closed, it means this one is open. This one is open. This K1 key is closed, and find the point where galvanometer shows no difference, and that point potential difference across the suppose J point. AJ gives EMF of this unknown cell. So E equal to VAB equal to KL1. L1 is the balancing length AJ. Now next, close this key K2 also, then current flowing through this one. Now this time galvanometer shows deflection at this point J dash. So potential difference across this AJ dash is not the EMF of this cell because the circuit is closed. This is potential difference. So, and this is equal to E minus Ri equal to KL2. And I is what? E by R plus R. R is external resistance, R is internal resistance. From these two equations, and after putting the value of I, you get the value of internal resistance as R equal to R L1 by L2 minus 1. This R is the external resistance which you are inserting in this resistance box. In this way, you can easily determine the internal resistance of a cell using potentiometer. So these two are very important applications: comparison of EMF of cell and determination of internal resistance of a cell using potentiometer, right? With this, I am going to end my video. Hope you like this series now. If you want this type of videos, please write in the comment box. Up to then, students, keep revising and stay tuned with this channel. Thank you.